Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to talk on the module Volatile and Non-Volatile Memories from the paper Semiconductor Materials and Devices. So students, let us see what we are going to learn in this module. First, various types of memories will be discussed. Second, a detailed description about the static RAM and the dynamic RAMs will be discussed in this module. Third, we will discuss about the read-only memory ROM. Next, a detailed description of serial access memories consisting of shift registers and queues will be provided in this module. Lastly, we will also discuss about the content addressable memory CAM and programmable logic arrays. So students, let us start with a basic introduction about the module. Memory arrays often account for the majority of transistors in a CMOS system on chip. So random access memory RAM can be accessed with a specific address and has a latency independent of the address. Whereas serial access memories have sequential accessing and thus requires no address. Another type of memory array is content addressable memory can be determined by addresses which contain data that matches the value. So the random access memory can be further classified as read-only memory ROM or read-write memory RAM. So another important classification is volatile and non-volatile memory. Memory is retained in volatile memories as long as the power is applied, while data is retained indefinitely in non-volatile memory. RAM is generally used with respect to volatile memory, while ROM is synonymously used with non-volatile memory. Volatile RAM, as you can see in this figure, students, it is further divided into static structures and dynamic structures. Static cells utilizes some form of feedback in order to maintain their present state. However, dynamic cells make use of charge which gets stored on a floating capacitor through the access transistor. Static RAMs or SRAMs responds faster and less bothersome, but they need more area per bit as compared to their dynamic counterparts or DRAMs. So non-volatile memories are categorized into 5 types of memory. Mask ROM, whose contents are hardwired during fabrication, which cannot be changed. Another one is programmable ROM, which can be programmed once after fabrication by blowing on chip fuses with a special high programming voltage. So next is the erasable ROM, we can say EEPROM, which can be programmed by storing charge on a floating gate. It can be erased by exposure to ultraviolet UV light for several minutes to knock the charge off the gate. The electrically erasable PROM, or we can say EEPROMs, are similar to ROMs but the data can only be erased in microseconds with the help of on-chip circuitry. Flash memories erases the entire block of data as compared to individual bits and thus are variant of EEPROM. These flash memories are successfully replacing the other commercially available non-volatile memories used in CMOS systems due to their good density and ease in integration with system reprogrammability. Memory cells can have one or more ports for access. So for both read-write memory, every port can be used as read-only, write-only, or both read and write operation. So consider a memory array containing 2n words of 2m bits each, where each bit is getting stored in a memory cell. So students, as you can see in this figure, which demonstrates the architecture of a small memory array containing 16 4-bit words. So the part A of this figure indicates the most basic design of a memory array which uses one row per word and one column per bit. So by asserting the word line, row decoder activates one of the rows using the address. During a read operation, the cells on this word line drive the bit lines, which may have been conditioned to a known value in advance of the memory access. So in order to detect the data, column circuitry is utilized by employing amplifiers or buffers. A typical memory array may have thousands or millions of words of only 8 to 64 bit each, which would be difficult to fit in the chip floor plan. Therefore, the array is often folded into fewer rows of more columns. So after folding, each row of the memory contains 2k words. So the array is physically organized as 2n minus k rows of 2m plus k columns or bits. Now the part B of this figure shows a two-way fold with 8 rows and 8 columns. The column decoder controls a multiplexer in the column circuitry to select 2m bits from the row as the data to access. Larger memories are generally built from multiple smaller sub-arrays so that the word lines and bit lines remain reasonably short, fast, and low in power dissipation. Since SRAM is the most widely used form of on-chip memory, so let us discuss the SRAM in more detail. SRAMs or static RAMs. They uses a memory cell with internal feedback that retains its value as long as the power is applied and has the following advantages. First, denser than flip-flops. Second, compatibility with standard CMOS processes. Third, faster and easier to use than DRAM. For these reasons, SRAMs are widely used in applications from caches to register files to tables to scratchpad buffers. The SRAM consists of an array of memory cells along with row and column circuitry. SRAM cells. A SRAM cell needs to be able to read and write the data and to hold it as long as the power is applied. An ordinary flip-flop could accomplish this requirement, but the size is quite large. A typical 6T SRAM cell is shown in this figure that can be an order of magnitude smaller than a flip-flop. The 6T cell achieves its compactness at the expense of more complex peripheral circuitry for reading and writing the cells. It contains a pair of weak cross-coupled inverters holding the state and a pair of access transistors to read or write the state. The cell is written by driving the desired value and its complement into the bit lines, that is bit and bit underscore b, then raising the word line word. It is read by pre-charging the two bit lines high, then allowing them to float. So when the word is raised, bit or bit underscore b pulls down, indicating the data value. DRAM. DRAM or dynamic RAMs uses capacitors to store their contents as a charge rather than in a feedback loop. Hence, the basic cell of DRAM is substantially smaller than SRAM, and it requires to be periodically read and refreshed so that its contents do not leak away. So commercial DRAMs, they are built in a specialized process using the dense capacitor structures. They offer a factor of 10 to 20 greater density than high performance SRAM built in a standard logic process. So students, as you can see in this figure, which shows a 1T means a one transistor dynamic RAM cell consisting of a transistor and a capacitor, where the cell is accessed by inserting the word line to connect the capacitor to the bit line. So when we are reading, the bit line is first pre-charged to VDD by 2 as shown in figure B. When the word line rises, the capacitor share its charge with the bit line, causing a voltage change delta V that can be sensed. The cell contents at X are distributed by read, so the cell must be rewritten after each read. So the bit line is driven high or low on a write operation, and the voltage is constrained onto the capacitor. So a few DRAMs drive the word line to VDD equal to VDD plus VT to stay away from a corrupted level when writing a 1. So in order to achieve a good density, DRAM capacitor cell must be as physically small. However, the bit line is contacted to many DRAM cells and has a relatively large capacitances C bit. Thus, the bit line capacitance is typically larger than the cell capacitance. So, according to the charge sharing equation, the voltage swing on the bit line during readout is given by delta V equal to VDD by 2 multiplied by C cell divided by C cell plus C bit. Let us now discuss the another type of important class of memory, that is ROM or read-only memory. So here the cells can be built only with one transistor per bit of storage. So a ROM is a non-volatile memory structure in which the state is retained indefinitely even without power. So a ROM array is commonly implemented as a single-ended NOR array. Commercial ROMs are normally dynamic, although pseudo NMOS is simple and suffices for small structures. As in SRAM cells and other footless dynamic gates, the word line input must be low during pre-charge or dynamic NOR gates. In situations where DC power dissipation is acceptable and the speed is sufficient, the pseudo NMOS ROM is the easiest to design, which requires no timing, so the DC power dissipation can be significantly reduced in multiplexed ROMs by placing the pull-up transistors after the column multiplexer. So the figure A shows a forward by 6-bit ROM using pseudo NMOS pull-ups with the following contents, that is, word 0 is 01010, word 1 is 011001, word 2 is 100101, word 3 is 101010. So the contents of the ROM can be symbolically represented with a dot diagram in which the dots indicate the presence of ones as shown in the figure B, and the dots corresponds to NMOS pull down transistors connected to the bit lines, but the outputs are inverted. Now let us discuss about the serial access memories. Utilizing the fundamental SRAM cells as well as registers, we can build a variety of serial access memories, including shift registers and queues. These memories avoid the need for external logic to track addresses for reading or writing. Now let us discuss about the shift registers. A shift register is ordinarily utilized in signal processing applications to store and delay information. This figure A over here demonstrates a basic 4-stage 8-bit shift register constructing from 32 flip-flops. As there is no logic between the registers, specific care must be taken that hold times are fulfilled. The RAM is arranged as a circular support with a couple of counters indicating where the information is read and written. The read counter is set to the first entry and the write counter to the last entry on reset as shown in figure B. On the other hand, the counters in the N-stage shift register can utilize two 1 of n hot registers to track which entries should be read and written. Again, one is initialized to point to the first entry and the other to the last entry. So the registers can drive this specifically without the requirement for a different decoder as shown in figure C. Now here the tapped delay line is a shift register variant that offers a variable number of stages of delay. Students Let us now discuss another serial access memory, that is queues. Basically here we will be studying about the FIFO and LIFO. Queues allows the data to be read and written at variable speeds. This figure demonstrates an interface to a queue. So here the read and the write operations each are monitored by their own clocks that may be asynchronous. The queue asserts the full flag when there is no room remaining in which we can write the data, and an empty flag is there when there is no data to read. So due to other framework delays, a few lines additionally gives almost full and almost empty banners to impart the looming state and end write or read request. The queue inside keeps up the read and the write pointers, demonstrating which information ought to be gotten to the next. So as with the shift register, the pointers can be counters or one of n hot registers. FIFO means first in, first out queues are generally employed to buffer the data between two asynchronous streams. So like a shift register, FIFO is sorted out as a round support. FIFO becomes empty on reset and both the pointers, that is read and write, are set to the first element. On a write, the right pointer advances to the next element. If it is related to catch the read pointer, FIFO is full. Now on a read operation, the pointer of read advances to the subsequent next element. Now FIFO becomes empty again on catching the right pointer. Next is last in, first out LIFO queues, which are known as stacks. They are utilized as a part of utilizations. For example, subroutine or intrude on stacks in microcontrollers. LIFO utilizes a solitary pointer for both read and write. On reset, the pointer is instated to the principal component and the LIFO is empty. On a write, the pointer is increased, and in this event, it achieves the last component and the LIFO is full. Let us now discuss another kind of memory, which is content accessible memory, or we can say content addressable memory, CAM. It acts as an usual SRAM that can be read or written given the address and the data, yet additionally performs the coordinating operations. Matching asserts a match line output for each word of the CAM that usually contains a predetermined key. So typical utilization of CAMs is translation, look-aside buffers, TLBs in microprocessors supporting virtual memory. The virtual address is given as the key to the TLB CAM. On the off chance that this address is in the CAM, the relating match line is stated. This match line can fill in as the word line to get to a RAM containing the related physical address. So students, this figure shows a 4x4 CAM array comprising of in the array of cells, a decoder and column circuitry. However, each row produces a dynamic match line. The match lines are pre-charged with the clocked PMOS transistors. The miss signal is produced with a distributed pseudo NMOS NOR. At the point when the match lines are utilized to get to a RAM, the monotonicity issue must be considered. At first, all the match lines are high, so during CAM operation, the lines pull down, leaving at most one line affirmed to demonstrate which push contains the key. Be that as it may, the RAM requires a monotonically rising word line. Let us now discuss about the programmable logic arrays PLA. They are exhibiting a normal structure to execute combinational logic determined in sum of products canonical form. So some finite state machines are formed by PLAs only if the outputs are fed back to inputs through registers. So PLAs were most prevalent in the beginning of VLSI when two-level logic minimization was surely known. However, multi-level logic optimizers were as yet juvenile. So they are thick and quick approaches to execute basic capacities and with reasonable CAD support are anything but difficult to change when logic bugs are found. So logic synthesis devices have significantly enhanced and now control logic is generally used. Also, pseudo NMOS PLAs disperse the static power, while dynamic PLAs require cautious plan of timing chains. So students, let us summarize what we have learned in this module. First, we discussed about the various types of memories. Second, a detailed description of static RAMs and dynamic RAMs were provided in this module. Thirdly, we discussed about the two memories, that is the read-only memory ROM and serial access memories, where we discussed about the shift registers and queues. In queues, we discussed about the FIFO and LIFO queues. Lastly, a detailed description of content addressable memory known as CAM or and the programmable logic arrays PLAs were provided in this module. Thank you.